will happen. Now, the tRNA molecules have to be charged, right? They're synthesized on the, if you look, go back here, it's totally back here, right? But if you look at here, the 3' end has the region where the amino acid is attached, so they're all charged in the 3' end. By the way, it's sort of interesting, as these guys are made, right? The tRNA molecules are transcribed, they're all transcribed without that CCA. And that CCA, the acceptor is added to all of them afterwards, and post-transcriptional mechanism. So there's an enzyme that takes and adds that CCA on there. It's not coded in the gene for these tRNA molecules. Anyway, it's there. But if you look, that 3' hydroxyl group, that adenosine, has to be charged. It's charged essentially by enzymes that are called aminoacyl synthetases. And those aminoacyl synthetases first, as they bind to the substrate, tRNA, the first thing they do is they activate that tRNA, they activate that hydroxyl group, they put on a good leaving group, so there's the biochemistry there. Hydroxyl is not a good leaving group, the phosphate is a good leaving group. So essentially that amino acid is activated by forming an aminoacyl tRNA, or adenylated amino acid. So you essentially put an adenine on there, AMP, monophosphate, generates a pyrophosphate. We talked about that before. Pyrophosphatases, they cleave it right away, ensures that the reaction goes this way. In this case, it doesn't really, it's not to drive the reaction this way so much, but if that hydrolysis of that pyrophosphate drives the reaction, it also prevents the reaction from going backwards. In this case, when these guys are formed, they're not needed to go back to the normal amino acid. So it sort of keeps them in this form until they're needed or until they're charged onto the tRNA. So the amino acid synthetases make this intermediate, which is this adenylated amino acid. And that adenylated amino acid then, that has this activated carbon there, is able to acylate tRNA, forming an aminoacyl tRNA. The aminoacyl becomes the acyl linkage here. So this is an aminoacyl tRNA, and the AMP is released AMP. So the only function of this ATP is to charge this guy once again with that phosphate, so it can be actively attached to that acyl group, forming the acyl linkage there. These tRNA synthetases, or these aminoacyl synthetases, are extremely specific molecules, are very specific. This blue here is one of the aminoacyl synthetases. You can see that it addresses that tRNA pretty intimately. They interact pretty close together. There is an aminoacyl synthetase, right? Each tRNA has a specific aminoacylate that acylates it. They recognize many different portions of this molecule. You can see the way that they attach, they can recognize. This is that L shape, so this is the acylation site up here. There's the CCA hanging off there. They're all intimately associated with that. This is the anticodon. They're sort of mapped right into that anticodon. They come along this stem. And in some cases, they do the other side. This particular cartoon here, or this isn't a cartoon, but this diagram that shows the crystal structure of both of these is for a aminoacyl synthetase that's a monomeric protein. Monomeric proteins kind of address the inside of the L like that. Some of the amino acid synthetases are also dimers or dimeric enzymes, and the dimeric enzymes address the backside. So there they're looking at the TCOU loop, and the D loop is folded over. They look at the backside of the stem, but they also look at here. This is a cartoon, and this shows, well, it's crystal structure also. But the class 1s are monomeric. They're the guys that are inside the loop. Class 2s just recognize the opposite side of the tRNA molecule. They look very similar, their structure is such that everything fits in there and they recognize it. This now shows you, it is a cartoon, it shows you where different amino acids address, or different synthetases address this. So essentially what it says is here, these are tRNAs, they all look the same. And if you look at an aminoacyl synthetase for adenosine, or for alanine, it recognizes this penultimate, or there's the CCA, this is the CCA, that's the adenosine, this aminoacyl in it. But this guy here, the 4th nucleotide in, the amino acid acyl synthetase for alanine recognizes that on the allyl tRNA. The anticodon down here, you notice that 17 or so of the amino acids, or the amino acyl synthetases, recognize this anticodon when they're putting on their tRNA. Notice serines not in there, alanine's not in there. Alanine tRNA or tRNA synthetase also recognizes something here in the variable loop, right, region of the particular alanine tRNA. So some of them are different. For instance, here's phenylalanine, right? Recognizes this part of the variable loop. So what that says is that this is the phenylalanine tRNA. tRNA synthetase that charges it, recognizes this part of the loop. So you can sort of see from this that they're all different. This next cartoon just gives you a couple examples. Remember I said that serine and alanine didn't recognize that anticodon? Here's the anticodon from protein. You can see that serine and alanine, not the tRNAs or the amino acyl synthetases that put that amino acid up on the end here. The serine-specific amino acyl synthetase that recognizes serine tRNA doesn't recognize that anticodon. It's sort of unusual. 17 out of the 22. That makes sense? Did I go too fast? I think that probably most of you have heard that. And you can just see, for instance, that the serine tRNA does recognize a lot of the nucleotides in the stem. It says, hey, this is serine tRNA, you need to put a serine on there. So the different amino acyl synthetases recognize multiple nucleotides in their complementary tRNA, but they then recognize different ones depending on the amino acyl synthetases. Y'all see that? Okay. Now the importance of all that, and this is the part that you should know, is that importance of all of this is that the amino acyl synthetase is essentially recognized. I thought I'd written it on the slide there. I'd written somewhere anyway. This recognition of the amino acid synthetases of their appropriate tRNA is essentially known as a second genetic code. You all know the first genetic code, right? Codon meets anticodon. The second genetic code is that amino acyl synthetase recognizes tRNAs. And why is that important? The reason is that the amino acyl synthetase has to put the right tRNA onto that, or amino acid onto a tRNA. We can take, in the lab, we can take any of the tRNAs and put on any amino acid we want. We can attach any, we can isolate it with any amino acid we want. And if you use that tRNA in a protein synthesis system, then the anticodon on the tRNA represents the codon on the messenger RNA. As long as those match, then whatever tRNA is up, or whatever amino acid is on there gets put into the protein you're making. All right. So the anticodon and the codon match, that's good, that's the genetic code. And on the other hand, whatever amino acid is up there gets shoved into the protein. In other words, protein synthesis doesn't recognize what amino acids on the tRNA. Right? Whatever's there. What does recognize it? The amino acyl synthase. So the acylation of that tRNA by the amino acyl synthetase is the second genetic code. It has to recognize the tRNA. If it doesn't, then protein synthesis is screwed up, just like if the anticodon didn't recognize the codon, you wouldn't build the right protein. Make sense? Second genetic code. So if you get asked what are the two genetic codes, you know. So the amino acyl synthetases also are a little bit like the polymerases, and they have two catalytic sites. They have a catalytic site where they put on the proper amino acid, but then they also have a site that edits it or that removes the incorrect amino acid. This shows you two sites. I don't know how we think that's true anymore. We do know that these amino acyl synthetases are able to check that amino acid that they put on and that they charge to be sure that it's the right one. We don't know how they all do it, but you can imagine how one does it, and we know that's true. We know it's true for the alanine tRNA. For one of the big ones. I forgot what anyway, these editing sites vary in size, right? So you can imagine if this is a small site, if this is an editing site for alanine TRA, and this is for alanine, and this is an alanine TRA, then the alanine would fit into this editing site and everybody's happy. On the other hand, if another amino acid was attached, a larger amino acid, it didn't fit into this site, it couldn't get into the editing site, then it would be processed away or cleaved off. Whether there's a second incorrect site, I don't know whether that's true or not. There are some models that call this the catalytic site, and this is the editing site where it checks for incorrect amino acids and cuts them off. I don't know that we're so sure about that anymore. Right? You can see here's the synthesis site, and there's a site where the amino acids are removed. Whatever, the important thing is that the amino acid synthetases are able to check the TRAs they chart to be sure they put the right one there. That's how important that second code is, and that the right amino acid's there. Okay, so